Now, it's good practice to consider the constant solutions of y before you actually start separating and then solving your differential equation. Now, think about why this is meaningful. If y is equal to some constant, so let's say y equals 5, something like that, then when you differentiate that, y dash is equal to 0. So if we've got some constant value of y that makes y dash equal to 0, then that function, y equals 5, or whatever it might be, is actually going to be one of the solutions of the differential equation. Now, the rest of the solutions might take some other fancy form and be quite complicated curves, but this special solution might be one of those ones that's a straight line. And we've seen these before. I've written down here, these constant solutions are generally horizontal isoclines consisting of horizontal line segments, and they're usually asymptotes of the other solutions. So we've found these before, but rather than picking them up at the end, spotting them at the start and thinking, well, I've got to make sure that my final solution actually includes these is really worthwhile. So the reason is that we might overlook them otherwise. So let's check for them at the start. This will make a little bit more sense in an example. Okay, so this example asks us to solve a differential equation and find two different particular solutions. Don't forget this notation means when x is 1, y is equal to a half, and when x is 2, y is equal to 0. Okay, so what we're suggesting is that when we look at this on first inspection, we should say, hey, what value of y will make y dash equal 0? Well, if y equals 0, that will be a solution. So we can note that first and say y equals 0 is a solution. Now, in our textbook, they like to say y equals 0 is trivially a solution. I don't think it's trivial. I mean, is it a solution or not? Now, they say trivially it's a solution because they're saying, hey, it's just one of the solutions. I think the best way to think of this is just to consider this is sort of the first case. This is one case of our solutions, because what we're going to do next is when we divide both sides by the function of y, we're actually going to put y on the bottom of a fraction. Now, if y is equal to 0, it can't actually sit on the bottom of a fraction. So it's almost like we're saying case 1 is that y could equal 0, and that will be a solution curve in its own right. Very simple curve. Obviously, it's a straight line, but we can still call it a solution curve. The second case is if y isn't equal to 0, and that has to be a case because if we're to put it on the bottom of a fraction, it can't be 0. So they say trivial it's a solution because it's a solution that actually doesn't work with the other solutions, if that sort of makes sense. So you could write is trivially a solution if you want to, because it sort of gets you around that idea of saying, hey, it is a solution, but it's not the only one, and we're looking for others. So now to look for the others, we've got our usual technique. We change y dash into dy dx. We divide both sides by, well, we've got a choice here, either y squared or negative y squared. Now, here's a hint. It's actually going to work out if I divide by negative y squared. And you'll see why in a moment. But again, don't be too concerned. It will work out if we keep the negative with the x. It'll just make our life a little bit easier with the negatives later on. So then on the other side, we've just got the x. And remember, we leave a bit of room. We put our equal sign in so that then when we integrate both sides with respect to x, we need to put our integral sign and our dx on both sides. The dx's on the left side always cancel. And now if you like, you can tidy this up and say, hey, we're actually integrating negative y to the negative 2 with respect to y. And of course, the integral on this side is always going to be very simple. So then over here, we're going to increase the power by 1, divide by the new power, and dividing by a negative when we already had a negative there, we'll cancel that negative out. And then on this side, we've got x squared over 2 plus our constant. Now, this is really 1 over y, isn't it? So if you want to write it that way, you can. You could do that on the next line. I'm going to save a little bit of space, be a bit cheeky, and just put it in there. Now, generally, we want to tidy up our general solution so it's got y as the subject. And at the moment, I've got 1 over y. So an easy hack here would be to take the reciprocal of the left-hand side, but to make up for it, I'd need to take the reciprocal of the right-hand side as well. Now, you'll notice that I don't have one big fraction here to take the reciprocal of. So if I want that, technically, I'd need to say, look, let's make this whole thing over 2. And that would make this 2c, wouldn't it? Now, we don't really want to call it 2c. We could actually call it d because it's a new constant. I think it would be tidier to leave that line there so it's really clear what I've done. I've got x squared plus c. On the next line, I could say, all right, I can do two things at once. I could take the reciprocal of this side. And over here, I could think, well, this is going to have a 2. So when I take the reciprocal, the 2 will end up here. And my x squared will end up on the bottom. But what I'm going to do is call that constant d, noting that c and d here would have to be two separate constants. So now I've solved my differential equation but I've just got the general solution. I've got one of the particular solutions here, and I've got two more that I've got to find. So for the first one of those, I need to say when x equals 1, y equals a half. So subbing that in, I've got half is equal to 2 over 1 plus d. So that means that 1 plus d must equal 4, and d equals 3. So therefore my particular solution is y equals 2 over x squared plus 3. So that's my first particular solution. Now the second one, we're saying when x equals 2, y equals 0. So subbing in here, I've got 0 is equal to 2 over 4 plus d. Now 2 divided by something can't equal 0, can it? So in fact I can't actually solve this one, and I'm feeling a little bit stuck here. Now the fact that I've thought through this at the very beginning is going to help me, because when I'm stuck and saying, well, I can't do 2 divided by something to get 0, I'm not sure what that constant's going to be, we can see that actually this line here, y equals 0, let's just think about what that looks like. It's just the x-axis, isn't it? This is the line y equals 0. It is a line that passes right through this point. Here's 2, 0 over here. So in fact, it is the solution that passes through this point. The usual working didn't really help me out, but the thinking that I did at the start did. So down here I would finish this one by saying y equals 0 is the solution for this one. So I've got two particular solutions. One of them is a bit special, and thinking about it at the beginning actually saved me from a bit of heartache when the working got a little bit awkward in here. And in fact, in that last example where I found myself finding an impossible solution there, I should have really written, this is impossible. I could see that it was, but write it down so that an examiner can see what you're thinking, because they can't read your mind. So obviously you've got to put all of your working on the page. So this is impossible, but y equals 0 is the correct solution that goes through this point. That's what you'd write, something along those lines.